Hello everyone, and welcome to the second video of the vectors topic. This one's going to be dealing with vector algebra. I am going to be introducing a bit more vector notation in here in terms of clarifying a little bit of how we represent vectors in terms of Cartesian coordinates. So if I go into the unit outline here, something I didn't introduce, which kind of should have been in the vector notation topic, but I've introduced it here because it deals more with vector algebra and vector arithmetic, is this way of representing vectors in terms of ordered pair notation and column vector notation, or also in terms of the perpendicular unit vectors I and j, and we'll talk about what a unit vector is over the course of this video. Then using those representations of vectors in terms of numerical values that denote a point in a Cartesian plane, we're going to be examining how the triangle rule and parallelogram rule kind of tie into being able to add and subtract components respectively. We're then going to introduce this concept called the scalar product, which allows you to do a couple of things. Most importantly, it allows you to test when two vectors are perpendicular, and you'll see that is very important when we are looking at real-world applications like closest approach, for example. If we have a boat that is traveling at a specific velocity in a specific direction, we can use the scalar product to determine the closest it will approach a specific point by examining when our velocity vector is perpendicular to the vector from the boat to that point. And we'll examine how that kind of looks and how that kind of works through a worked example over the course of this, in the next video, in real-world applications of vectors. In this video, I'm just going to go over how you apply the scalar product and how you calculate it in both the component form and the sort of multiplication of magnitudes and cosine of the angle between them form. I know that this is all coming across as a bit abstract. I'm just mentioning a couple of things, but it hopefully will make sense over the course of the video. So let's get straight into that. Okay, so this video is titled Vector Algebra, but realistically it should be titled Vector Arithmetic. The reason why I've labeled this Vector Algebra is because when you look at real-life applications of vectors, you often use algebraic methods to determine and compute certain algebraic values. And in that video, we're going to introduce more vector algebra than we really are in here. So realistically, this video should have been titled Vector Arithmetic, but regardless, let's get started. So, as I mentioned in the previous video, we can label vectors in a geometric sense, and we can denote them on a Cartesian plane. So if we have an x and a y axis, we can have a vector here, and this vector will be a directed line segment towards a specific point, and this point will have an associated y coordinate and an associated x coordinate. For the sake of this argument, let's say that is 4 and 4. And so this vector we can label with the brackets 4, 4. I use these specific triangular brackets to indicate that it's a vector as opposed to a coordinate where I simply label it as 4, 4. This is sometimes used to represent vectors, but I find it a bit too confusing because it's too similar to coordinates, which isn't generally the case for vectors. A vector indicates that it's a directed line segment in that direction, whereas a coordinate is just a point on a Cartesian plane. So this is a component form representation of a vector. Okay, we can also equally write this as 4, 4 in this way. This is also similar to combination notation, but it is not combination notation in this case, obviously, and being able to determine whether something is a vector or something is a combination depends on the context of the question. So if it's a question about vectors and it uses this sort of notation, then obviously it's going to be dealing with a vector as opposed to a combination. Now, if I consider this vector here, I can also consider my components in terms of horizontal and vertical unit vectors. And what a unit vector is it is a vector with a magnitude of 1. In this case, the most common unit vectors that we use to denote this in component form is the horizontal vector in the x direction, which we denote as a vector I, and the vertical vector in the j direction, which we denote with a j. Okay. And so in this case, we have 4 I vectors in the horizontal direction and 4 j vectors in the vertical direction. And if we sum these two together using our vector addition in the geometric interpretation head to tail, we can see that 4i plus 4j is equivalent to my vector v, if I label it as vector v. Okay? So this is ordered pair notation. The one here is what I am talking about here. Column vector notation is this. I have also defined the unit vectors I and j. As you can see here, I represent vectors with bold notation, but if I am writing them, I write them with a tilde, I and j. And I can also express a vector in component form using the unit vectors. Basically, this ordered pair notation, column vector notation, 4i plus 4j, or whatever the coefficients are, all mean the exact same thing, and they are different ways of denoting a vector. Importantly, if a question phrases a vector in either the ordered pair notation, the column vector notation, or the unit vector sort of component form of I and j, then always write your final answer according to the notation that is used in the question. So if your question uses column vector notation, make sure that your final answer is also in column vector notation. Commonly, when you are doing your, when you are generally computing, I find it most useful to use the column vector notation because it's very easy when you're adding vectors together or subtracting vectors from each other that you accidentally subtract or add the wrong components. And I find that using column vector notation is a lot easier way of keeping track of what to add and what to subtract when you're doing that. So now that I've been talking about addition and subtraction of vectors in component form, I will introduce how that kind of works. So if I have a vector A here, and this has a 3 in the horizontal direction and 4 in the vertical direction, and I have another vector like this, let's say this is vector A, this is vector B, this is a vector with 5 in the horizontal direction and 1 in the vertical direction, so I can write B as equal to 5i plus j, or 5, 1, or 5, 1. I can write A as 3i plus 4j, or 3, 4, or in column vector notation, 3, 4. Okay? If I am adding my A and B, using my triangle rule, I can see that it will look something like this. And again, I have 5 in this direction, 1 in this direction, I have 3 in this direction, 4 in this direction. Cumulatively, if I consider my vector here, the resultant, maybe I'll do that in a different color. The resultant here in blue that I've drawn here, this is equal to A plus B. If I consider the horizontal and vertical components of each of these, I can see that the horizontal component is comprised of this first horizontal component added to the second horizontal component. So in this case, my horizontal component will be equal to 5 plus 3, which is equal to 8. So I have 8 in the I unit vector direction. In the vertical direction, I know that I can add these two together. And so in the vertical direction, I have 1 plus 4, which is equal to 5 in the j direction. So cumulatively, my vector is 8i plus 5j. And that is equal to A plus B. Okay? Similarly, if I have my vector A and I multiply it by 2 and I have 2A in this case, all I'm doing is I am taking my two components, which are in this case 3, 4. Oh, sorry. They are 3, 4, multiplying each of those components by 2 to get 6, 8. And so this is my scalar multiple of my vector A. So if I'm doing vector addition and vector subtraction in component form, essentially I'm just adding my x components and adding my y components. So these two add together and the y components add together, as I have shown here, and that is the geometric interpretation of why that is the case. And similarly with scalar multiples, you're just multiplying each of the components to themselves. each of the components by your scalar multiple. The last thing I want to introduce is the scalar product. The dot product, also known as the dot product, it can also be known as the scalar product, or dot product. Both of them are the same. And if I take a vector A and I dot it with a vector B, what that is equal to is the magnitude of A times the magnitude of B times cos of the angle between them. Importantly, if I'm dealing with the angle between them, what I mean is that they are either tail to tail, so they're tail to tail, or they are head to head. Okay? So if I am looking at tail to tail, in this case, for these two same vectors, A and B, if I'm looking at head to head, it will look something like this. And if you kind of consider it here, you can see that that angle is going to be the same as that angle due to alternate angles. Hopefully that makes a little bit of sense. But that is the important thing about the angle between them. This here does not classify as the angle between them, but this does. Okay? So the angle between the two vectors for the scalar product is referred to as the tail to tail, or the head to head angle formed between those vectors. If I consider what that kind of represents in a mathematical sense, if I separate A and B a bit more obviously, so I have A and then I multiply that by B cos theta, and let's say I have my A, I have my B. Or let's say this is A, let's say this is B, and this is theta. Then B cos theta, the magnitude of B cos theta, is the magnitude of the component of B in the direction of A. B cos theta. And that is because cos theta will necessarily be equal to whatever this value is here. So let's label this value X, divided by the magnitude of B. So this value here will therefore be equal to the magnitude of B times cos theta. So what the scalar product is it's what we refer to as the projection of B onto A. That is the component of B in the direction of A multiplied by the magnitude of the vector A. And because these are both magnitudes, they're both scalars. And because they're both scalars, the dot product is a scalar, and that's why it's also called the scalar product. Now, in terms of the dot product as well, another thing is that the dot product is also equal to the x components of each of the vectors multiplied together, added to the y components multiplied together. So if A, in this case, is equal to A1, A2, and B is equal to B1, B2, that implies that A dotted with B is equal to, in this case, A1 times B1 plus A2 times B2. And so this is the component-wise way of determining a vector. This is a sort of, if you're given the magnitude and the angle between them, you can calculate the dot product in this way. Okay? And so this is easier when you're given the vectors in component form. This is easier when you're given the magnitudes and the angle between them. The scalar product is also very helpful to determine the angle between the vectors if you rearrange it in terms of cos theta equal to A dotted with B divided by the magnitude of A times the magnitude of B. If you use component form to determine your scalar product here and divide that by the magnitudes, and the magnitudes are easily calculated by using Pythagoras' theorem, a1 squared plus a2 squared. Then using Pythagoras' theorem, you can divide by each of the magnitudes and find cos of the angle between them. Taking the reverse cosine, you can find the initial angle. The reason why you can use Pythagoras' theorem is because you're dealing with horizontal and vertical components, your i's and your j's. And so your vector, if you include the horizontal components and the vertical components, they will form a right angle triangle. If you have your vector A, you have your horizontal components, you have your vertical components, and you have a right angle, just like this. All right, a couple of important properties of the scalar product that you should know. The scalar product is distributive, meaning that if you dot A with b plus c, that will be equal to a dot b plus a dot c. Another important property of the scalar product is that it is commutative, which means that a dot b is equal to b dot a. It is also commutative for scalars. If I have lambda a, which is a scalar multiple of a, dotted with b, I can equally write that as lambda of a dotted with b, and I can equally write that as a dotted with lambda b. Okay? I think those are the most important properties. Another thing is that the scalar product of something multiplied dotted with itself is equal to the magnitude of that vector squared, and that's because cos of the angle between two of the same vectors is cos 0, and cos 0 is equal to 1. Okay? And so if you have a scalar product where you are dotting a with itself, you're multiplying the magnitudes of a twice and multiplying that by 1, giving you the magnitude squared. So those are the properties of the scalar product. That's all for this video, and I'll see you in the next one. Thanks for watching. Bye-bye.